Okay, this is the day we learned to count to higher than 2. We'll spend a lot of time on counting to 3, which is the cyclic group with 3 things. And we're going to talk about how the group theory gives you the modes for something like that and classifies them. And there's a great deal of physics that wasn't present in the double oscillators, which I will review just briefly from our lecture 6, and that was when we introduced that first. But today I also want to do the product table derivation of the so-called regular representation and discuss the conjugation symmetry, some very basic things that are true for all applications of group theory, and then go right into the spectral resolution of a 3x3 Hamiltonian for a three-dimensional oscillator that has symmetry. And the whole business of orthocompleteness, all of the stuff that we learned about projective idempotence, that's going to come up here. And it's the way that group theory can be done in the most efficient way I know of, and applied to the quantum mechanics or classical mechanics that arises from systems of symmetry. The dispersion function, we didn't have anything like that because there were really only 2 points in the K-space for a double oscillator. Now we're going to have more of them, particularly as we begin to consider things like hexagonal symmetry, which we'll do toward the end of the lecture. So that will pretty much be today. Now in lecture 12, which follows this, we have a generalization of beats. You're going to see a little bit of that, but we won't describe it much as we're going through this. So let me just very quickly remind you what we did when we first considered the C2 group, the group whose multiplication table consisted of a 2x2 square in which the elements unit and reflection, in this case the B reflection, the bilaterally symmetric reflection, was in question for producing a spectral decomposition. And the object was to diagonalize a spring matrix. This is the classical problem. And the picture of the system that was being described is here. And the symmetry operator was just simply the mirror reflection that demanded that everything on this side was mirrored over here precisely, and that the masses were the same. So these 2 spring constants had to be the same. And it didn't matter what the constants were after that. So the product table, as you saw in that discussion, gives you immediately a group table. You simply put down 1s wherever the element in question is appearing in the product table, and that's true here for the unit operator and for the reflection, bilateral reflection sigma b, which appears in the off-diagonal parts of the table, so that's what the matrix looks like. Now, we're going to see that generalized. That's called producing a regular representation. Regular meaning permutations that are regular, and those are permutations that move everything in the set that's being permuted. Now, our main job, and this is the second slide of the review, is the spectral decomposition of that group. So each element of the group, and now we're going to have 3 elements for C3, 6 elements for C6, and so on for all of the cyclic symmetries. The idea is that those group operators can be expressed as a linear combination of orthogonal idempotent operators, operators whose square gives themselves back again, and whose products between any difference projection operator or idempotent gives 0. And we saw that 1 plus the half sum and the half difference between the elements of the C2 group was all there was to that symmetry that came out of the minimal equation for that. So we're going to have to go through a minimal equation, obtain a spectral decomposition, then we're good to go. We'll have all of the group theoretical, shall we say, coefficients that you need, the so-called character table. I want to familiarize you with the old-fashioned notation so that when you read the literature, including textbooks on applied group theory, that you can make a connection of this.
What do you mean by considering sigma b as an operator and as a ket?
Well,
I cannot get.
That's really, thank you for that question, because that's really the essential thing that we're doing in all of our applications of group theory, including all of that stuff that had to do with the Euler angles and the crank. It was easy enough to label a group operator by a crank. That's what it does. But to use the Euler angles, you were labeling the various coordinates, the various position states, you see. So when you drew a ket and put alpha, beta, gamma in that, you meant that you had in your mind a state of orientation for some object, in particular a spin vector perhaps, or this ball on the machine that we have here. So that's going to be true of all the groups we do, including the simplest one, which is C2. So the idea is that the different states that are available for this one, which are not shown here, but well, they are shown here. This first state right here, the 0 state, what we would call X maybe as opposed to Y. This one was called 1. This was the binary labeling, you remember? We're going to be doing trinary labeling very shortly here, so everyone knows about the bits in a computer, but very few people make computers out of trigonal bits, you see. We're going to be doing that for any number eventually. That's what Cn means, n possible settings of a register. But the states, those register settings, here's one of them, and here's the other. Okay. Well, the name we're going to give to this one is just plain old 0. That's the computer-like notation, or just the state 1. Okay. 0 is the operator 1 times that, and we'll often, this is an identity sign here, we'll often replace the operator sitting here acting on the original state. We'll simply put the operator, which in this case is an operator that does nothing, inside the ket. Then, when I go to apply a symmetry operator to get another state, in this case there is only one more, and that's this one, okay? So the idea is I imagine this state has this mass at the equilibrium position, which is its origin, and this one has moved a unit distance in a positive direction, which means it's pushed into here, it's pushing the spring in right there. So that's what this state means. It's a unit state in terms of motion. This would be an angstrom or a centimeter or something was appropriate, and we would just call that number 1 and this number 0. And then the reflection of that by this reflection operator is to simply put it over here. You see, that's the idea of this. And this is a state that's actually located, you can write it as a -1. So when I do a reflection, like is shown there, I put it in the ket. Okay, does that answer your question? It's certainly an important thing. Because then you see, we're going to also, if I do a projection on that, I'm going to put the projection inside. I won't do that very often, but anything I do to the ket, I might just go ahead and stick it in there for shorthand. That means you have to know where your origin is and all of that. Okay. Let's see if there's anything else that I need to say. I think that, unless you can think of another question, this is the main thing that we're after, is a spectral decomposition. We'd also like to be able to invert those That is, give the projection operators in terms of the group operators, you see. But if we play our cards right, that's an easy task. We are still in a unitary world here. And finally, this is the last slide. This produced for us a similarity transformation that diagonalized the original spring K matrix, and would do so for a Hamiltonian as well. And they're analogous for that reason. So what we're really looking for, that most people know and love in the world of quantum mechanics, is a diagonalizing transformation, which I call D-tran. And there's the notation for the D-tran representation using the bases that we have here. Well, it turns out that that transformation matrix is called a character table. So this is the C2 mode phase character tables that we looked at ever so briefly, written in phasor notation, but when you look them up in the library in a group theory book, you're going to have a table of numbers, usually complex numbers. We'll see a table of 3 very quickly today in our lecture as we work with a triple mass system. But this is the stuff that we've done already. So you're getting your first look at a chi table. The notation will be the Greek letter chi for character, which really means the characteristic values, the eigenvalues of the group operators. That's where the name comes from, I think, we can safely say. Okay, so we ended up with an even mode, 0 mod 2. For what we had was a kind of a pseudo momentum. We're going to see more clearly what that is when we get 3 things or 4 things or 100 things going. Then it's really going to mean something. Right now it's kind of puzzling that I would use the name momentum for a quantum number here. And also M stands for the magnetic quantum number in a situation of quantum mechanics that you when you deal with orbitals, okay? And we're going to get those by group theory too. So all this is working to make a world that's much easier to live in theoretically. And then this thing here was a power of the operator P, but it also was a position point. Your origin and then one other point in the lattice. We're going to have, as I say, 3 things, so there'll be 3 points where a mass equilibrium position is, and then we'll be good to go using all of the same ideas that made this. So this is the simplest possible group theoretical application, and it's the simplest group that exists, C2. That's not trivial. You can make a table for just one by itself, but no one, they call that the trivial group. Poor thing, what a terrible name for someone. But anyway, that's the where we are right now. So what I want to do is do the C3, just the product table. And I'm not even showing what it goes with, but basically I'm just lining up elements, and I'm going to have r to the 0th power. That is, r will be r to the 1st power, which will be the same as r to the -2, as we're going to see. And then there'll be r squared, and that's the same with a triangle as going backwards 1 step. So we're going to have a modular arithmetic for both the exponents and then the m numbers that come out of the eigenvalue structure of these operators. So this product table here, I call it a G-dagger G product table because one of the things that you have to do in order to make a useful regular representation is put, if you're going to put the element G here, you want in that same position to be G-dagger or G-inverse. G-dagger equal G-inverse for all the operators we're dealing with here, because we are in unitary subgroup, a unitary subgroup, okay? So we set it up so that if I put an element G here, I put its inverse here, then I put this one here, that's the inverse of R squared, which happens to be R to the first power. That way, I get a unit element on the diagonal of the table. Once you've done that, you now can read off those elements into matrices that will obey that table. And that's the regular representation of the group in a very simple way described. Same as we had with the C2. Okay? So, once you've got that, then you say, okay, the Hamiltonian matrix, or the spring matrix, I'm doing classical problem, I'm going straight to quantum mechanics today, but we'll have plenty of examples where you could see what it would look like for a classical situation where this was a spring matrix as opposed to a Hamiltonian. But in any case, the idea is that a Hamiltonian can have this many parameters, 0, R1, R2, and these, now they're numbers. They're numbers, though, that are coefficients of the element whose power is indicated by the number, in this case, 0, 1, and 2. So that's kind of neat. Basically, we're saying all the matrices that you would make for a space completely described by this group would be right here. And the idea is that we're representing each power of this element R that is generating this group. So we just have one more than we had before. It's really not that hard, but there's some complexity associated with having three things that 2 doesn't have. And so what we're thinking of course, is some sort of mass arrangement, and I've made it simple. I've just made it so the masses slide in and out radially. Okay, and then there's a spring connecting them that lets them slide, but they have to slide this way, in and out. They're not allowed to move that way. We'll get into a whole full molecule, ozone molecule. You can move this way and rotate, do all sorts of things. We'll get to that eventually. This is a very restrained sort of classical object, but the classical object is modeling waves that live in 3 different points. So we're playing the same game we were with the U2. We're going to be playing with a subgroup of U3 now that is quantum mechanical. Shall we say Hubbard model for tunneling in graphene or something like that, you say? That's what we're starting here. Okay, and we're making a mechanical analog of it. Okay, so we have these coupling constants. They relate to particular operators. Once again, we're going to have states that are labeled by operators, these operators. And what I've indicated here are some of these constants that are grayed out may change values if the C symmetry is broken. So if I were to take this R0 and make it a little bit larger, or maybe this one right here, this would be some sort of, I could have a spring attached here that I didn't attach to the others, or I could make this R1 and R2 the coupling constants, and we're going to distinguish between the effect of this one on this one and the effect vice versa. You see, we'll have an arrow indicating that this one is affecting that one, and then another R for the going backwards. So that's something that comes with what's called the gauge. If you make all of these parameters, active and not the same. In any case, the ones that are grayed out, and normally this one is going to be the conjugate of this one, but if it isn't, the symmetry is broken. And we'll discuss that later on. Now let's do the case where, now the equilibrium 0 state, as before, would be the one that has all of the coordinates here, x0, x1, and x2, are probably not showing up too well on the video there, are all 0. And so this thing is in an equilibrium state right there, okay? And the other thing that we didn't have to worry about with the C2 example, because we had a B minus IC and then a B plus IC on the other side, that was conjugation symmetry. Here we have three pairs that will have to be the conjugates of each other in order to have a Hermitian symmetric Hamiltonian. Now it's possible to break that too, to make them not equal, okay, make them not conjugates of each other. It's also interesting, and we'll talk a little bit about that. But just having them be complex is already interesting because they have to be complex to get a current going through, get that C-type motion. We have to have an imaginary part for these in order to get something going in a tunneling model like this. So far so good. It's somewhat sketchy. Okay, yes. We're going to have to, you know, put some meat on this in order to put some numbers into this to make it simple. But I will point out that I'm numbering these things as a point that is 1 modulo 3. So this is number 1 over here. Then down here, this is 0 mod 3. So I start here really and go to there, okay? There's 0, that's the original state. And then we're going to have operators that take some excitation of this thing and move it nearby, or move it over here. Those are the two things you can really do. And then if this is 1 mod 3, then this is 2 mod 3 over here. So 0, 1, and 2 are the numbers for those masses. And so far I haven't thought of changing the actual values of it. That would be another way to break the symmetry. Lots of ways to make this thing not C3 symmetric.
By operator R1, just we move one of them.
This fat R1.
R1.
Okay.
Rotation of 120
that would be
an
an operator
120.
that moves the
Whole system.
whole thing. Okay.
And we are symmetric.
What a better way to say
see
it
any
was.
change.
That's the symmetry.
Yeah.
We're constructing the molecule starting off with 1 and nothing but symmetry.
This,
And if it was
yeah,
a symmetric
this,
molecule, we're good.
this molecule has the symmetry where if I do a 120-degree rotation, it doesn't change. You see? Or do it again, doesn't change. Okay? Or do the inverse of either of those. Okay? It doesn't change. And the reason for that, first of all, is that we're going to have this thing right here be the inverse of that. This thing here be the inverse of that, and so forth. So those two operators, R1 and R2, they are inverses of each other. R2 is just R1 in. And you can see that if I do a rotation that takes me over to here and then do it again and get over to here, I could have just gone this way with it, you say. And then these are the operators that are going to take something that has non-zero wave function or activity or displacement and move that displacement over to here, you see. And then while it's at it, whatever displacement was here is going to get moved to there, you see. And whatever was here is going to get moved to there, you see. So these are operators that are global. They do the whole thing. Okay? And that was the same thing with the 2, remember? The sigma b not only affected the number 1 or the number 0, right? It affected both of them by going like that, right? This one is doing that, but it's doing it as a rotation. Now, the group that we're doing, C3, is an abelian, that means commutative group. If you want to consider reflections, and they are there, you see, that's a bigger group, which we're going to tackle separately. Okay? That's called C3 vertical reflection, C3V. Or if you were to have a 180-degree rotation here, that's called D3. But that makes you have 6 operators altogether, which is 3 factorial, which is the number of permutations of these 3 things. And that's definitely a non-abelian group, you see. So I'm playing this game with just trying to solve this problem with the least symmetry, which is this one, C3. So when we get, in a few lectures later, we're going to tackle the non-abelian groups. But first, let's get C3, C4, C5, C6 under control, you see. Then we can do D3, D4, D5, and the world grows very quickly after that.
You mentioned permutation. I just can't help but think of, since you already have these labels,
right,
permuting the labels and using that cycle notation that we picked up in math.
Right, and that's the group theory of permutation groups, the whole family, is one of the most beautiful pieces of mathematics that man, in my opinion, man has ever discovered. The various ways that you describe the representations of that is incredibly powerful. So then we're getting into things that you can do with group theory that no one even conceived of, let alone did. I mean, it really is, that's where it gets its power. But let's just do this first. And this is just Fourier analysis that we're doing. We're doing a discrete Fourier space. And I think we always can do a better job at things if we take the simplest cases of each new development first. So here are the p equals 0 unit base state, along with p equal 1 unit base state, and the p equal 2 unit base state. So the 0 base state is when the original one at the bottom here, we've chosen that to be the number 1, but it's really number 0, okay? And its coordinate is now equal to 1. All of the others are still on the equilibrium positions. And obviously, if I let this go, the whole thing's going to start vibrating, so this is not something that's going to stand still like that is supposed to do. So here's unit displacement. Now I do an operation, r not to the 0th power, which describes this one, but r to the 1st power on the original state. I get the next state, number 1, p equal 1 base state. Okay? Or if I want to be really precocious, I do the operation 1, 2 to 2nd power, going the other way. In any case, I take this and move it over to there. And that's what I call, with a column vector, 0, 1, 0, whereas this one is 1, 0, 0. That's the ket represented in what you might call the regular basis, the basis of this matrix that the Hamiltonian is being written in, and all of the group operators are being represented. And now finally we represent the third thing that we call number 2, and that's the confusing thing about using computer notation: 0 modulo 3, 1 modulo 3, 2 modulo 3, to characterize each of the states. So I haven't done it yet, but I would put this state equal to a ket with an r inside. And this one, to answer your question at the beginning, I would put r to the 1st power inside there. I might even go r to the 0 just sitting in there to, make it clear. Obviously, it's easier just to write the number. Okay, but all of those notations are possible. These are the base states right here. And it's every bit of the arithmetic of this group table is modulo 3. We'll keep emphasizing that and then show better examples later on. Is there anything you can think of to ask?
For operators, we didn't talk about the displacement of the math, but for this...
Remember, we only have radial displacement allowed, okay? So there's little rods in there on which these slide frictionlessly. It's the ideal radial oscillator. Now, obviously we could be doing this with one in which the only thing they could do is slide on a ring, right? That would be a whole different problem. So this might be what you would call the radial triple oscillator.
Yes.
You could also have a ring around here where they would go like this on the ring, and it would be called the angular. Or if you're thinking the way the solid state physicists do, that you're going around a lattice here, this is the one that has the transverse motion, right? And the other one is longitudinal oscillation. These are, names you've probably heard, just describing a straight line of atoms in a lattice, right? Ours is a straight line in some sense, but we wrap it around, right, to make it cyclic. Later on, we'll make a connection between things that are straight and things that are tied. That's a very interesting subject in itself. The topology of crystals is just now being discovered. Just now. It's all these years we've been working with crystals. And now, finally, the group theory is growing up. Okay. Now, the idea is that we can spectrally resolve the Hamiltonian if we resolve R. Just do that one R, since H is a combination of powers of R. R to the pth power. Okay? So the R symmetry implies a cubic R cubed equal 1. Or R cubed minus 1 equals 0. I'm talking about operator stuff here, but I'm thinking matrices. Okay? And that's going to be resolved by 3 roots of unity. Now, where do those guys come from? That's an important part of this discussion. Okay? Complex numbers make it easy to find cube roots of 1. Okay? 1 is e to the 2 pi I times any integer. That m later will be our magnetic quantum number, perhaps. But in any case, if I go and I take the cube root of z, then I simply get e to the 2 pi I, that integer, divided by 3. So there is what the cube root of 1 looks like if z is 1. Okay? So it's this guy we're going to be playing with throughout the discussion of the representation theory for this group. And when we have n particles, we're going to be doing the nth root. So we'll have 2 pi I m divided by the symmetry index, n, which is usually the letter that's used to describe the number of particles in your lattice. Okay? So having this thing cubed to 1 means that we have an equation of algebraic 0 equal the cube of r minus 1, and that factors very nicely into these 3 roots, the 0, 1, and 2. That is m equal to 0, 1, and 2. So those are the roots that we're going to be working with. And it doesn't hurt to just write that, first of all, but then we need to show some pictures of where those complex numbers are in the complex plane. But that's the basic idea, is we're going to be working with those 3 complex. This one is real, but these 2 are conjugate complex numbers, conjugate of each other. And I just see a typo there. No, I don't see a typo because I've got a 2 here. But if I were to take that and replace it by minus 1, then I'd have e to the I times 2 pi I over 3. And this would be e to the minus I times 2 pi I over 3. So that's the way it should be. Okay, so those are the 3 numbers that are going to appear in a character table for this group. But we're getting ahead of ourselves. I want to make sure that we see the operator manifestation and resolution of that character table. these numbers here, the chi's, refer to characters or characteristic roots of the symmetry. And there they are. That's all this stuff is playing with those numbers and the matrices that they will eventually represent. So we know there's a projector made out of these group operators, r squared and r the first and r the 0th, 1, and 2nd power, okay, such that the operator r hitting them gives you the character, that is the root, the eigenvalue of that particular element. And those are going to be the things that make up the eigenvalues of the Hamiltonian. The way we do things here, okay? And we know also, just from the way these work, and we'll see this in several ways, that they are orthonormal, that is, the idempotent relation holds. Both when the m's and n's are equal, then you just get the operator back again. When they're not, we'd better see a 0.
Sorry.
So we're going. This is basically the projection theory for that matrix that consisted of 0s and 1s, 3x3 matrix. And we also know, and this, remember, this was sort of magical when we did it with the ABC matrix that we talked about, a 1, 2, 3, 4 matrix that we talked about when we were doing eigenvalue review.
Does Hamiltonian have matrix representation?
That's right. You see, we're kind of doing things backwards here. Let me back up, because that is an important question.
This is.
You see, I'm saying, instead of you give me a matrix, and then I go look up what its symmetry is, and then I try to find all this stuff to diagonalize it, I say, let's play it backwards. Let's say, and this is more obvious, that all the possible matrices in the whole world that have this symmetry that obeys this simple closure here, they're all going to look like this. You see, they're all going to be linear combinations of the regular representation of this group table, this multiplication table. So we're playing the whole thing backwards. We're saying these are all the Hamiltonians that I could possibly have that has this symmetry. Now, what did we do when we played the U2 game? We said, I need a Hermitian generator for the unitary group U2. I needed a Hermitian Hamiltonian 2 by 2. That forced us to make the diagonals real, because it has to have the Hermitian transpose relation. That is, the diagonal element had to be its own conjugate, and so did the other diagonal element. So that was A and D. Then we had the possibility of 2 real numbers, B and C, right? One of them made the bilaterally symmetric Hamiltonian, and the other one, the C, made that curly guy, right? Same game we're playing here. We're just laying out the most parameters this thing could have. And it's really quite a number. It's not just 3 real parameters. As we're going to see, this one has to be real. But these two can be complex conjugates, you see. And that will get currents going in this thing. Okay? Does that help at all?
Just, I want to solve the eigenvalue problem with this Hamiltonian, but I cannot put, I mean, I don't know what are R1, R2 to find the eigenvalues, as you found.
Oh, what we want to do is we want to get a formula for those eigenvectors and eigenvalues for any set of parameters. Now remember, that's what we finally did with A, B, C, D, right?
Mm-hmm.
We finally ended up, it took a while, but we ended up with a very elegant formalism that gave us both the eigenvectors, right, and the eigenvalues. And all the dynamics, right? We're trying to do the same thing here. Okay? Does that help a little bit?
Yeah.
Yeah.
There's similarity between this and ABC.
Yes.
R0.
Yeah, these are, yeah, I could,
not
exactly.
R1 and R2.
We could have gone A, then I have to have a B plus IC, and then a D plus IE, right? There. Okay, and that would be it, because I couldn't make these different from that, you see. That makes sense? Yeah. It's only slightly more complicated than our ABCD. But the flavor is very different. Yeah. Okay, so let's go back and see how this is going to look. Here's the way our elements, 1, r to the first power, and r to the second power are going to play out. First of all, completeness. You've got to have that. Okay? Then, we also have to have spectral decomposition of each of these elements. So let's take r itself, r to the first power. Okay? So here's r, and the first power barely shows up. That's terrible blue. But it's just going to be the characteristic roots. Chi0, Chi1, Chi2. Okay? And we're numbering them in this this trinary fashion, not binary, because we got 3 things. Trinary fashion, 0, 1, 2, modulo 3, just like the powers. Okay? And those will be the eigenvalues that sit in front of projection operators that we're going to call 0, 1, and 2. Same idea. Okay, so those are the M numbers, momenta, if you will. And then I square this. Well, that means I have to square that. This one will usually be 1, so it didn't do anything. But I do have to square this one. That will not be anything but a complex number that's different from this number in general. Okay? So there's our group spectral decomposition right there. Now the rub is, how do you invert that? Because obviously I want to get the projection operators in terms of the group operators. What we just did says, well, if this is going to work, it has to be. That was a definition that we extracted from our knowledge of the eigensolutions by projector. You see, we've done the mathematics for that. Now we want it to work for us. Okay? So the question is, how do you turn this inside out? How do you invert this? Well, here's a picture of these numbers. Here's Chi0, which happens to be, I'm putting down here Chi0 star for reasons that we'll see later. Here's Chi1 star. I'm being very careful with making things so they correspond to the most common literature. This is, you know, even this group is a tripping point for the ordinary methods of doing group theory. And people like Schrodinger hated group theory because they said, I don't need this to, you know, find this cube root of 1 or whatever I need. I've got Fourier theory, I can use that. The heck with this. Okay? So I've got to be careful and make sure that things jive with the standard conventions. So I'm showing you the conjugates here because that's what I'm going to use for the projectors. Projectors are simply going to be made out of conjugates. Because this is a unitary linear combination here, I can invert it simply by transposing and conjugating. And that's what we do. So what I will first of all point out is, though, that the things that I call characters that correspond to what's in most text, it'll almost always be displayed this way, where these wave numbers, M for momenta, come in 0, 1, modulo 3, so do the powers, which tell you what points you're doing. So this is space, this is per space in the wave Fourier analysis. So it's now we're going to work with these numbers. And it's going to be the conjugates of these numbers that we actually look at when we invert and make P0 equal to some combination of R a 1, r to the 0, r to the first power, r to the second power, and so on for each of the projectors. Once we've done that, then we've got eigenvectors and eigenvalues, everything that we possibly can need, dispersion relations, they all come out. Okay, so these three C3 character conjugates, psi star equal e to the I mp 2 pi of 3, those have a notation in Fourier analysis as being wave functions of space, spatial points. And they're labeled by momenta. So e to the I km, this is km times rp, actually divided by the square root of 3 in order to be normalized. That is very conventional notation for wave functions. Maybe not the same letters and indices or anything, but that's the basic idea of psi of x in Fourier analysis. And that's what we have here. The characters star, the representations of the group that are tabulated, star, are wave functions. That convention is followed since Wigner, and pretty much always. Now there's some people that goof it up, but I'm saying the majority of the literature would write a psi instead of a chi. But our psi, their psi, and our chi star, very similar except for normalization. We don't need normalization. We've got operators. They're going to be taken care of. Okay? And this is a picture of the character table written out as waves. So we already know what the eigenwaves look like. The eigenwaves look like things that have phasors set in pointing at the points of an equilateral triangle. Okay, and that's what we're going to be making our eigensolutions out of. And there's one of them up there in the running in the animation that is you can get this animation by clicking on this in the lecture slides. It's to wave it. And we're working on making it easy to get that particular wave to come up. If you do this, a wave with 12 things comes up. But we'll get around to fixing that. And later on in Mull Vives, where we do the whole problem, this will come up with just as much ease as that. Okay, so now what I have to do is do the inversion. Okay? And here it is. Basically, what I'm doing here is I'm saying, okay, if 1 r to the first power and r to the second power is written like that, okay, and I'm even going ahead and putting 1 to the square here, which is, you don't need that, but nevertheless, here are the numbers, okay, and I just simply have to do a Hermitian conjugate of that. If it were states, that's what you'd do. I would start out with the state 1, the state r to the first power, the state r to the second power, equals 1 over the square root of 3, these various sums here, and I put the square root of 3 on this side so that these numbers are the only thing in play on the right-hand side of those equations, okay? So those are what we might call ket relations, and inverting this is easy. Just do the Hermitian conjugate. And our operator norm will be 1 over the number of them. So this is what you get, that extra norm, but then I just put in here what was 1, okay, ends up here. I have this one right here, star, this is psi star, that's this thing right here. You see that it's been conjugated. This one here, been conjugated. These guys right here all have minus signs. This has a plus sign, this had a minus sign before. That's it. Okay? I can go through and solve this thing, you know, yourself, but that gets really laborious for anything bigger than 3. In fact, it's already laborious with 3. So this is the kind of thing we're going to do for all of our CN groups. Once you've done 3, you've done them all, as far as this kind of arithmetic goes.
What is 1, 3 and 2, 3? 0, 3, what are they?
Okay, that's the name of the base states, okay? The base states that are going to be our momentum states. They're the states that are going to be projected by these guys, okay?
Oh.
Okay? They're going to be the actual waves. That's what we're after. These are states where all the activity is piled up in one place. And they're linear combinations of our eigenstates. Okay? So here's the power number, the point number, 0, 1, and 2 here. That's the momentum number, 0, 1, and 2 modulo 3 for the momentum states, which we'll look at very shortly here. Okay?
Can you come back to the picture of the 3 spring?
Base states?
Yeah.
Yes, because
I want to know.
it was for the radial case, right? So let's go way back here.
Sorry.
That's okay. That's what this thing is good
Yeah,
at.
here.
There you go. And this state is on equilibrium for these two, which is
Are these 1? Sorry, are these
And
1
that's
and
one.
2? Oh, this is 1.
yeah, it's off by 1.
1 unit.
Okay, positive by 1.
Is it the ket 1?
And it would be written as ket. This one's ket 0 because
Ket
it's
zero.
the 0th mass, the 0th point that's been pushed off center. And then this is the ket number 1, the second state, okay, has been pushed off by unit 1, okay? x1 equal 1 here, x0 equal 1 here. All the others are 0, right?
What is 0, 3? Can you show me, I mean, what is 0, 3 in this picture?
This would be 0, 3 here.
And
For
what?
point. That's for point, okay? Now, you want to see 0, 3 when it's momentum,
Momentum.
then I have to take this plus that. So that one's easy, right? That means I pull them all off equally and let them go.
1, 3? It's a
1, 3 is a little more complicated because I have to take this one plus e to the 2 pi I over 3 plus e to the 2 pi I over 3. So they're out of phase. You're talking about a moving wave like that. That's what it's going to look like. Okay, does that help?
Yeah.
Okay, so let's go forward and actually get these guys to show up. The character table is already telling you that's the momentum 1's state right there. You see, it's saying take this guy times 1, take this guy times e to the minus 2 pi over 3, take this guy times e to the plus 2 pi I over 3. You see, these coefficients, these chi coefficients are the ones that tell you how do you phase the displacement. They're the coefficients right there written in complex variables. Real axis, imaginary axis. Okay? And that's what I mean by a wave. M equal 1, say. Okay? M equals 0 is really easy. It's just a sum of them all. All those 3 you were looking at, right? This is hard to see. That's why we have all this computer graphics, to make sense of that. And this one is just a conjugate of this. If this was a wave going this way, this will be a wave coming the other way. So we really only have to learn one of these, and we'll have a pretty good idea what it is. So there is a picture of a snapshot of this wave. Okay? And you can see, just from looking at this thing, who's ahead. Okay? This guy is ahead of this one. So this is a wave going this way. this one down here, you see, now this one right here is behind, this one is ahead of that one, right? This is, you know, early in the morning, 8 o'clock, this is already 12 noon, right? So this one is a wave moving that way. Remember when we talked about the phasing, right? So, if I freeze, and we might as well swing over here and do that right now. If I freeze this wave in some position, okay, stop time, okay, now you're looking at a wave where this one is at almost 6 o'clock, but this one is back at about 2:30, right? So this one's ahead, right? That means that this wave is going that way. When I turn the time back on again, whatever is here is going to be realized here at a certain, you know, just a little bit, that fraction of a cycle, 1/3 of a cycle later, okay? And then this one is ahead by the same amount of this one. This one still has to get over there, right? To be this one. And this one has to get down to here to be this one. And so forth, and then this whole thing wraps around. This has to be identical to this one. This whole thing is wrapped around. Okay? Now here's the imaginary part of the wave, which is making, this is the real part of the wave, this is the imaginary part being plotted there. So you can see imagination precedes reality by 1/4 in all waves that are linearly connected like that. So we'll get that going again. And the thing is, you see, what's great about this program, I think I just drag it right here, is I can drag it. You see, that's the way time is going to go. Okay? So right at this moment here, this one has only a real part, whereas this two have opposite imaginary parts, and so forth. So that's what this is what we want to understand. Once we understand it with 3, actually, it becomes easier as you put more in. Because you see, we have already calculated, just by doing this, the solution for any number of atoms. We just put atoms on this line right here. But that has to be demonstrated. This is why it's almost always better to do mathematics discretely first, and then try for the continuum. Okay? So when we were doing this conjugation here, to make these states, that's what it amounts to, you see? This is our projector right here, okay? So that's what goes there, that's what goes there, that's what goes there, and so forth. And remember how the normalization of an operator have to take the square root of it to get a normalization for the thing. So basically you take the projector, multiply by the square root of 3, and end up with the square root of 3 in the denominator. So those are the actual momentum states, the wave momentum states, obtained by this group theoretical analysis. Now we got to smooth this off some, but the basic idea is here now. And again, here's the picture of it. So we will be using momentum times some quantum number. I should say momentum quantum number times x, kx. This is basically e to the I kx, where x is given by the coordinate 0, 1, or 2 in some units, which we'll straighten out all that. But right now we're doing it in the most elemental possible way. And I should warn you, I may have actually misspoke before, but all of these phasors are turned. You're used to a phasor with real axis this way and imaginary axis this way. All of our phasors are turned for our transverse waves. If we're doing a transverse wave, I want real up. So the real part is where you see it. The imaginary part is 90 degrees ahead in the way we do things here. That's clockwise. That's because phasors go clockwise, you see. Okay. So I want to mention, again, two distinct types of modular quantum numbers. The points, or power, of the operator r to the pth power. Label oscillator position point P. That's along the top of these transformation matrices, diagonalizing transformation, the D-tran matrix, or the Hamiltonian. But character tables here are very powerful. The M equal also 0, 1, or 2 modulo 3, just like these. That is the mode, momentum, I should say magnetic mode momentum. M. You use M 3 times in physics here. Okay? And we'll be using M when we do spherical harmonics and stuff in relativity, all kinds of stuff. We use it. Okay? M or P obey modular arithmetic. So sums or products equal only 3 numbers possible, 0, 1, or 2. Modulo 3. If it's 30, then it's 0 modulo 3. So 30 is 0. So is anything that's a multiple of 3. And then anything that's a multiple of 3 plus 1 or plus 2, you can call these the remainders. Well, they're characterized by the first and second, not the zeroth, first and second rows of the momentum table. But the same is true for the positions, because the idea is this thing is wrapped around. It's a topological entity, very simple one, ring. All right, now, I do want to say that this stuff again. If you want to really make a wave function of position x with k vector km, then you got to do a little bit of adjustment here. You got to turn this mp into mp times 2 pi over 3. You've got to turn that into an e to the I kx. Okay? Forget the normalization for the time being. So we have lattice position vectors xp equal some length, lattice spacing, times p, however many points you've got. And we have a wave vector, okay, that's 2 pi times the momentum over 3, that's the whole lattice. Well, that becomes 2 pi times lambda m. The wavelength lambda m is 2 pi over k, you should probably remember that formula. That's 3 L's, lattice spaces, over m. That's the total length of the circumference of one of these rings divided by the momentum, whatever the momentum quanta is. Okay, so this is where you make the connection to ordinary sort of elementary quantum mechanics wave notation. Okay? And when we apply an r to the pth power to something that is at a position q, and these are integers again, modulo 3, I mean to talk about the position q plus p. So that's what I'm doing. I'm moving the thing around the circle by p steps. Okay? That implies the inverse of this, which is r to the minus p power, of a bra, which is rp dagger, okay, should be equal to q plus p. That implies that rp operating on a bra gives you minus. Okay? So the action of RP on an M ket is inverse to the action on a coordinate bra. And you always put the coordinate bras this way and the momentum kets this way when you describe something like this. The x is on this side, not sitting on the right like it is in the Schrodinger picture. Okay? So I'm leaving norm factors out. Here is the psi momentum m, that means k vector number m, a position x whatever, minus p dot l, that's given, that's the actual wave function I would get if I did an rp on a km. I can either act this way or I can act this way. Now right now we're acting this way, so I put a minus sign there. That's what this wave function is. So that's e to the I km times the position that you started with minus whatever the position is to get to point P. That's xp, that's L times the integer P. So here's where we really settle the bookkeeping we're going to use for all of our groups, but C3 is the first one that's non-trivial enough to require complex numbers in general. Okay? So here's the x. There's the m. And that's gotten by doing a translation by p units of your momentum. So you take your wave and go click, click, p times to make this wave. And what you've done is you've turned it into something that has a position minus p sitting on the other side. And it gives you this phase factor. So each time you do a transformation by p's power, you get a phase factor, e to the minus I km dot x. That's your character. The actual wave function star. That's why we're being so persnickety about keeping the things in the right order. So this is the effect on a momentum state. This is the eigenvalue of the r to the p operator, the characteristic value. It's the wave function e to the I kx conjugated. Well, this is something you're not going to memorize right away. But I'm trying to give you a roadmap to it so that it's easy to remember. The rules have to make sense, you see. Okay, so two distinct types of modular quantum numbers, as I said, are the position p's, points, powers, okay, and the magnetic mode momentum m's, and either obey modular arithmetic. Let's just go through a few examples. M equal 2, P equal 2. Okay, this is an example. Okay, so I have this thing here, e to the I m times 2 pi over 3, that's pm, to the pth power. Okay, that makes me a product, mp times 2 pi over 3. Okay, if they're both 2, I got 4 times 2 pi over 3. All right, now I can break that up into 1 times 2 pi over 3 times e to the I 3 times 2 pi over 3. Well, that's just e to the 2 pi I is 1, so there's what we're interested in. That's e to the 2 pi I over 3. That's row 1, if you want to label these roots the way I have here. All right? 2 times 2 mod 3 is not 4, it's 1. The remainder of 4 divided by 3 is the way to remember that. Okay? Here's row 2 square. We're talking about something that is 5 mod 3. That's 2. Be the fifth equal row 2. We're just talking about basically number 6 mod 3 is 0. Okay? All of that is something you've got to get used to. Okay? Minus 1 mod 3, that's 2, and so forth. Minus 2 mod 3 is 1. They reciprocate nicely. So the way to think about it is imagine going around a ring that's addressed by these points, okay? For regular integer points, say that's your origin, you'd go 1, 2, 3, 4, 5, and forever, and then minus 1, minus 2, minus 3 forever, okay? But if we're going to do a modulo 3 thing, every time I get to something that's divisible by 3, I put down a 0, right? So there's your little table to see. Minus 3 is 0 mod. Minus 2 is 1 mod 3. Minus 1 is 2 mod 3. 0, no problem there. Okay, 1, no problem there, no problem there. Okay, there's where we change, right? Okay, then 4 is 1 more than 3. 5 is 2 more, and so on. Okay, that's probably the easiest way to say all this, but they all have to be in your head there. We really only have about 10 more minutes here to do some work with this. Here I'm saying e to the I mp over 2 pi 3 must always equal e to the I mp mod 3 times 2 pi over 3. So whenever I say mp, I mean mp mod 3. Whatever arithmetic I do, I'm going to always want to say how I've specified my modularity. Now it might be that you don't want to always have positive numbers, you see. You might want to just slide this over a little bit and have something like this, you see. Let's just work with 1 and minus 1 and forget about 2. Okay? Well, you use 2 once, but that's it. That's called the centered Brillouin zone way of doing things, whereas this is an extended zone thing where you go off the positive direction. We'll get all that back later on. Okay, let's look real quickly again at the C3 group jargon structure for various tables. Here's our character table written in several different notations. And you can see we're always talking about a chi sub m with a power p, and the power here being 0, 1, and 2. That is giving us a chi to powers minus 2 because they're conjugate to, in other words, chi 0, chi 2, and chi 1 have a conjugate relationship, which is shown there. And the best thing to do is look at the phasors to find that out. Now, we're treating these things as, and this is notation we don't really need right now, but we will in the non-abelian groups have representations that are characterized in character tables that are matrices, that aren't just 1 by 1. These are all 1 by 1 matrices. So irreducible. I mean, well, how can I get any more reduced than a number? No problem. It's when you have a matrix that you're trying to sort of diagonalize, then you use this symbol D. And again, this is standard notation that I have to get you used to. We don't really need it all the time because we're doing everything with projections. But these characters you see are representations of this group. These numbers here obey the group table for this cyclic group. And so they are representations in that sense, and they can't be reduced any further than they are, so they are irreducible representations, trivially so. And we'll get that later on. So this is the kind of table that you might want to get used to seeing, and that's where the actual representation symbol is sitting here. But they mean characters, you see. These numbers are the things that we've been calling the chi's. With abelian groups, there's no difference between the D's and the chi's. And if there is, the author has missed up on some phase or something. They should be the same. Identity representation obeys any group table. The other ones are non-trivially obeying this group table of multiplication, group multiplication. Okay? So I think that takes care of that. Okay, let's get some physics going here. If you want to find the eigenvalues, and that means the wave dispersion functions, for a Hamiltonian that has a tunneling between 3 points that is given by these parameters, and 2 of them are complex, so that's altogether 5 parameters, then here's the answer. End of story. You see, this is so powerful. Once you realize the Hamiltonian is a linear combination of these, and you know these are the eigenvalues, you see, for each m eigenstate quanta, each momentum, if you will, you're done. That's it. But you got to massage that answer. You got to take a critical look at it. Okay. First of all, there's the zero right here. Okay. Well, if that's the case, I get that. That's out of it. That's just one. Okay. Then this thing is plus and minus, so I got a cosine there. Okay. And for the time being, we're going to assume that these are real. So we're going to put a little r down there for both of these. All real Hamiltonian. This is the block Hamiltonian, the most elementary example of it. And this is the most elementary block dispersion function, but we only have 2 points to worry about. You can see that either m equal plus or minus 1 or 2 is going to give me the same number. So here's writing the whole thing out. There's the Hamiltonian that we're working with that has 3 parameters out there that are all equal. And then this one has to be a real because it's a Hermitian operator. Now realize you can solve a problem with non-Hermitian things. The H could be some sort of weird servo mechanism that has complex numbers in here too. And in which case you're going to get complex numbers right there and inside these exponents, so and you're going to get a solution that blows up. But let's just stick with the things that behave. A right-handed moving wave and a left-handed moving wave are being shown here, and then the scalar standing wave is being shown here. And this is the dispersion function that we would calculate for any m, or any n, that's n, remember, n equals 3 for this thing. We're going to be doing that with more than 3 very shortly here. But this is the dispersion function that it is a projection of an equilateral triangle that's sitting on its one of its points, equilateral point. Okay. This is an exciton-like dispersion function. It has a curved bottom. It's got a parabolic for low k bottom. We don't care about anything but one point, so this is sort of superfluous. But anyway, that's an approximation for if m was, take a fraction in there, and you do that. When we talk about n equal 12 or 36 or 100 or something like that, we're going to have that many points on this curve, making us a very complicated oscillator. For classical k values, we need the square root, okay, k eigenvalue. We need the square root of this to be a frequency. Remember that? That was the, the little dichotomy we had between k classical and quantum Hamiltonian, square root, okay? Then you get a thing that looks like this. That's the square root of this. It starts out linear and then bends more than this one does. Okay, so it has a long straight region here whose slope is the velocity of phonon. That's the velocity of sound. This one, very bizarre, exciton-like behavior compared to what we're used to when we talk about oscillations in mechanical systems. So here you see a really big difference between the physics of a more than 2-dimensional oscillator, 3 in this case, and a classical setting and a quantum setting. In any case, this dispersion function, square root of that, comes out to be a sign, but it's a sign that is the absolute value. We don't let it go negative. So the dispersion function, frequency versus k, comes out in a first power, linear at low m, if we have more than just the m equals 0, and then this is called the Brillouin zone right here. We only got that in the bottom. We only got top and the bottom of this for a triple thing. So triple's pretty simple, almost deceptively simple, but this is the basic idea of it. And standing versus moving waves. Standing waves possible if H is all real, no curly stuff allowed, okay? So I'm making the thing so that all of the eigenstates are real, okay? That's easy to do, because one of them is a conjugate of the other. So I can add or subtract half sum or half difference, but I'm normalizing, so it's square root of 2 inverse of the sum and difference. They have to be 50-50 mixtures of a wave going clockwise and a wave going counterclockwise in the setting that we were showing in the animation. Okay? So this is an example of a standing wave, which I will try to show up there in just a minute here. But you can see that because the eigenvalues don't care whether you've got the moving wave this way or this way, they are equal, because cosine of minus x is equal to cosine. That's a degeneracy. That means there's higher symmetry in this problem. Whenever you see a degeneracy, almost always means the symmetry has changed. And this is a beautiful example of it right here. So these two eigenvalues are equal because of that. Plus and minus doesn't make a difference. Cosine's even. So whether you're doing the k eigenfrequencies or these, you're going to have a degeneracy out there at the high frequency. So here's what they look like if you sketch them. This is the radial standing waves, all real. Okay? This one you don't have to do anything to. That's just a breathing mode. Okay? That's this guy right here. Everything in phase. But the other guys, there's a symmetric and anti-symmetric mode, which are you going to try to get one of those if you can? One of those standing waves. The moving waves are easy. The standing waves sometimes are a little troublesome. But here we see this one has symmetry. In the sense I could bring in a reflection symmetry and say, hey, yeah, it has that. In and out. Okay? Well, this one goes in, this one goes twice as far. And then when it comes back twice as far, this one goes out 1 unit, both of them. And then this one where this one doesn't do anything, but this one comes in while that one goes out. That's called asymmetric stretch. So I can sort of wave my hands to what these things are doing. If I had 3 hands, I could do a better job. But this one, I've got enough hands because that's all it's doing. And then, of course, this one's symmetric, but it's symmetric in all 3 places. So those are the radial standing waves. Here are the angular standing waves if we were doing that problem. This thing would be just rotating, or librating, as they say. This one right here would be going twice as far this way, while the other 2 went into it. And then these 2, leave that one alone, and they would go like this. Okay. So depending on which one you look at, some of these make sense and some don't on different days of the week. But that's the basic idea for the standing waves. Now, I think we are out of time and maybe out of battery. If you have a standing wave going on the thing, you could probably point the camera at that just to get it. It's running very slowly so you can see what it looks like. And I believe I can also turn on the molecule that goes with that, right? You might go ahead and do that if you can, TC. That way we'll make connection with when we actually are doing some molecules. It would be show the ring molecule. Yeah, see if it'll go. There you go. Okay. So that is an animation that you can play with on your own if you click on the things that go with this. You see there is the triangle at the bottom, and the thing at the top is going twice as far as the two things at the base of the triangle. So that's sort of an inverted view of what we had in the picture on the slides. And you can see the phasors for a real wave are either in phase or out of phase with their neighbors. And that means they can transfer no energy. You know, a good lesson to realize. Whereas the moving waves are transferring as much energy to the next neighbor as they're taking from the one behind them.
Go to a moving here. We used to about zero one of these compounds out.
That's the Fourier control. We have to explain that. That's a very nice thing. You can set the either the coefficients that have to do with momentum or with position, and really get a feeling for a Fourier transform of 3 dimensions. That's what we've got here. But we've really solved for any number of atoms. We have just solved that problem. And that's what's so cool. Once you've done 3, you've done it.
Oop, go back.
4, 5, 6, 7, and 8.
Which one was that? Which one of these?
This is a
That is a moving wave.
m equals 1.
Yeah, that one is a moving wave, which is what we were looking at back here. Okay?
Oh,
So that's just one of these dots, plus one I think he's got turned on.
One wavelength fits on.
Yeah. So he's looking at this one, I believe,
Mhm.
and it's a right-hand moving wave. It's imaginary. You see, look where its imaginary part is. That'll tell you where it's going.
oh,
Imagination predicts future.
oh.
Okay?
Shall I do the m equals -2? We'll show the other one here. We'll zero that out.
Zero everything.
Okay.
Yeah, because otherwise you almost always have a residue. Yeah. There you go. That should be the other one. And then start it. There she goes. Yeah. So now the wave is coming toward me. It's going to the left. Now the other application for this, which covers our country and certainly yours, is 3-phase. The cables that you see high above the desert are 3 in number. And that's what they're doing. They're all 120 degrees out of phase with each other. And that's a very efficient way to transmit power. It was discovered by Tesla in turn of the 19th century. A little later than that, actually. But that particular one, if you could see the oscillation on those 3 wires, you could tell which way the phase was going. It's making a corkscrew around those triplets. So who says group theory doesn't have an application that's worthwhile? So does that make sense, Mohammed?
Yes.
You can see how Tesla could do all this without group theory. He didn't need it. He had pictured in his mind the phasors, the real and imaginary part, the actual amplitude, and then the derivative with respect to time of the amplitude divided by the frequency makes a circle, a circular phase space, which is called a phasor. And it's a very different definition of phasor than you find on Star Trek or one of those things, but it is a very useful representation of a complex number, which lets you see how energy is being fed and who's ahead and who's behind. Whoever's ahead has to feed anybody that's connected to them that's behind. So it's, yeah, we gotta
It just
call it a
died.
day here.